This course module covers the technical fundamentals of guided wave radar. After completing this module, you will be able to understand dielectric constant and its influence on guided wave radar measurement. Explain how guided wave radar technology uses the time-of-flight principle of operation to measure level. Describe how guided wave radar measures level and interface level. Understand the universal nature of the technology. Identify the influence of process variables on guided wave radar technology. Guided wave radar is one of the fastest growing technologies because of the installation flexibility and application capabilities. But before we study the MT5000 series of guided wave radar devices, we must understand how the technology works. Dielectric constant is a material constant applicable to all materials in reference to air being equal to 1. The measurement describes the relationship of how much the capacitance of a capacitor changes when filled with a certain material in relationship to a capacitor filled with air. The dielectric constant of the measured material is always more than 1. Dielectric values can be grouped into categories as illustrated here. Additionally, dielectrics can be grouped as high dielectric and low dielectric. Most materials with water content are considered high dielectric, while materials which are plastics, polymers, or hydrocarbons are considered low dielectric. The dielectric constant of the material helps you to determine the choice of the probe, the installation options, application limitations, and it is the first variable to address when using guided wave radar. Guided wave radar uses the time domain reflectometry measurement principle. Microwave pulses are created and propagated down the probe or cable of the device. When the microwave pulse makes contact with a change in dielectric, a reflection is created. X radar sends and receives 64,000 pulses per second and provides 2 output readings in that time. The higher the dielectric of the material, the greater amount of energy reflected back to the transmitter. Using the time-of-flight principle, we measure the distance to the surface and back, and then divide by 2. Let's look at a few examples of the use of guided wave radar. In this example, we will look at the use of guided wave radar in a high dielectric fluid, such as water. With the vessel empty, the radar signal travels to the end of the probe, and a large reflection is created. As the vessel is filled, the energy reflected from the liquid surface is so great that the level is easily seen, and the end of the probe is no longer visible. Another application example is the use of guided wave radar in an interface application. As with the last example, when the tank is empty, the radar signals travel to the end of the probe, and the end of the probe is seen. Assuming an oil as the top fluid and salt water as the lower fluid, we can see that the radar behavior is the same. We get a reflection from the upper product surface, but because the dielectric is low, the signal is also able to travel to the interface surface and create an additional signal reflection. Guided wave radar makes this measurement with no moving parts. As you've already learned, guided wave radar uses dielectric constant as the measurement variable. So what influence do the other common process variables have on guided wave radar? Guided wave radar is unaffected by the following variables: changes in pressure, changes in temperature, changes in material density. Additionally, guided wave radar also perform well in misting, dusty, or heavy vapor applications, turbulent services, foaming applications, light coating, sparged services, some flashing services, services with some emulsion present, changes in angle of repose in solids applications. Due to its universal nature, guided wave radar can also be installed in a wide variety of installations and can successfully be used in the following applications: external chambers, open vessels or sumps, storage vessels, process vessels, or spheres, top vessel entry or even side vessel entry to replace DP, horizontal cylinders, reactor vessels, or plastic vessels, in solids or liquids. Now let's summarize this learning module. So, what have you learned so far? You've understood the dielectric constant and its influence on guided wave radar measurement. You can explain how the guided wave radar technology uses the time of flight principle of operation to measure level. You can describe how guided wave radar measures level and interface level. You've understood the universal nature of the technology, and you can identify the influence of process variables on guided wave radar technology.